40% of the universe is essentially invisible to human senses. Not because it's too far away, but because it's buried in data we already have and simply can't see with our own brains. For the last few decades, astronomers, geologists, biologists, and climate scientists have been quietly building some of the largest datasets in human history. Sky surveys that catalog billions of galaxies, Earth observation satellites that measure the planet's atmosphere, oceans, and land surface every few days, genome projects that map the DNA of thousands of species. If you printed all of this data out, you'd get a stack of paper that would reach well past the moon. And yet, hidden in that blizzard of numbers are patterns we never noticed, rare events we never recognized, and entire classes of objects that we didn't even know to look for. Not because we're not smart enough, but because our brains evolved to track a few moving animals on the savannah, not tens of terabytes of multidimensional sensor output per night. This is the bottleneck that modern artificial intelligence is starting to break. To understand why, it helps to be specific about what AI is actually doing here. When we say AI in science, we're usually talking about machine learning systems, algorithms that can learn statistical patterns directly from examples, instead of being explicitly programmed step by step. A classic example is a neural network, which is roughly inspired by how networks of neurons in the brain process signals. You feed it many examples of, say, galaxy images labeled by their type: spiral, elliptical, irregular, and over time, the network adjusts millions of internal parameters so that the right output label tends to fire for the right input image. This is called training. Once trained, the same network can look at a brand new galaxy and classify it in a few milliseconds. But the real power is that it doesn't just memorize. It learns the underlying structure of the data, subtle combinations of shape, brightness profile, color distribution, that correlate with certain physical properties. And that means it can notice when something does not fit any of the patterns it has seen before. Think about the modern sky surveys like the Vera C. Rubin Observatory's Legacy Survey of Space and Time, or LSST. When fully operational, it will image the entire visible sky from its location in Chile roughly every 3 nights, generating about 20 terabytes of raw data every 24 hours. That's more data than every photograph taken by humanity up to the year 2000, collected every single night. Hidden in that torrent will be transient phenomena, things that change quickly. A star being torn apart by a black hole, called a tidal disruption event, a supernova exploding in a distant galaxy, an asteroid briefly blocking the light of a star as it passes in front, a stellar occultation that can reveal the asteroid's size and shape. Some of these events last minutes to hours. If you notice them a day late, they're already gone. No committee of humans, no matter how dedicated, can stare at millions of new images every night and say, "This pixel changed. That flickered. This moved." Machine learning systems, on the other hand, are built for exactly this. They learn what normal sky variability looks like and then raise an alert when something deviates from that background. At a technical level, these systems look at multiple dimensions at once: brightness, color in different filters, how an object's light curve, its brightness over time, rises and falls. They might use convolutional neural networks, originally developed for recognizing cats and faces in photographs, to scan astronomical images pixel by pixel and spot the characteristic expanding shell of a supernova remnant or the streak of a near-Earth object. Or they use recurrent or transformer-based models, originally designed for language, to interpret sequences of measurements such as how a star's light dips and recovers as a planet transits in front of it. Instead of reading a sentence one word at a time, they read a light curve one timestamp at a time and learn the grammar of planetary systems. What used to take astronomers months of careful manual inspection can now be flagged within seconds of the data hitting the ground. We've already seen the power of this in action. The Kepler and TESS space telescopes have collected brightness measurements for hundreds of thousands of stars, hunting for exoplanets, planets orbiting other stars, using the transit method. A planet crossing its star blocks a tiny fraction of the star's light, often less than 1%, for a few hours. In the raw data, this looks like random noise. Early planet discoveries relied on painstaking human-designed algorithms and lots of human eyeballs. But in 2017, researchers used a deep neural network to reanalyze Kepler data. The network was trained on known transits and learned the very specific shape that a real planet transit typically has. A smooth, symmetric dip that repeats with a fixed period, as opposed to the irregular blips of stellar activity or instrumental glitches. The system didn't just confirm planets we already suspected, it found new ones that the earlier pipelines had missed, including Kepler 90I, a small hot planet in a system that now ties our own solar system with 8 known planets. Same telescope, same photons, but a new layer of pattern recognition extracted more universe from the exact same data. This is the key idea. AI is not magically creating new information. It is compressing and reorganizing the information that's already there, in ways that make physical meaning pop out. You can think of it as a kind of information telescope. A regular telescope changes the spatial scale. Distant galaxies become points of light you can resolve. An AI system changes the statistical scale. Buried correlations and rare patterns become things you can actually notice and reason about. And crucially, these systems don't get tired. They don't get bored. They don't skip a weird-looking curve because their coffee is getting cold. They applied the same level of attention to the millionth data point as to the first. This same story is playing out closer to home, in Earth science. Our planet is currently surrounded by a kind of digital exoskeleton. Fleets of satellites like the European Sentinel series, NASA's Terra and Aqua, and many others, continuously scanning the surface in multiple wavelengths. Visible light, infrared, microwave, even radar. They measure sea surface temperature to within fractions of a degree, track atmospheric gases like carbon dioxide and methane, monitor vegetation health using indices like NDVI, the Normalized Difference Vegetation Index, and detect subtle changes in gravity that reveal how groundwater is shifting beneath our feet. The result is petabytes of data per year. Traditional climate models and remote sensing techniques already do a lot with this, but they often have to simplify. They might average over large areas or longer timescales just to keep the computation tractable. AI, especially deep learning, lets us keep more of the fine-grained structure. For example, detecting methane leaks from space used to be extremely difficult. Methane is a potent greenhouse gas, and large leaks from pipelines or industrial sites can significantly affect local and even global warming. Spectrometers on satellites can pick up the spectral fingerprint of methane, specific wavelengths of infrared light that methane absorbs, but the signal is weak and cluttered by clouds, aerosols, and the complex reflectivity of the ground below. Machine learning models trained on known leaks and controlled experiments can learn to disentangle all of this. They effectively learn this exact combination of spectral features under this type of surface and atmospheric condition usually corresponds to a real methane plume. That allows them to scan huge areas and flag likely leaks in near real time, sometimes down to the level of individual facilities. Again, the physics, how methane absorbs light, is the same. The AI just lets us exploit that physics at scale. And AI doesn't only see what's already obvious, it can reveal phenomena that were simply too subtle or multi-layered for our older tools. In oceanography, for instance, mesoscale eddies, swirling vortices of water tens to hundreds of kilometers across, play a major role in mixing heat, nutrients, and carbon dioxide. They affect weather patterns, fisheries, and the rate at which the ocean absorbs human-produced 2CARs. But eddies are hard to track globally because they're born, evolve, and die on timescales of days to months, and they interact in complex ways. By training neural networks on satellite altimetry data, tiny variations in sea surface height, often just a few centimeters, scientists have built systems that can automatically detect and follow eddies over time. The networks learn the characteristic spiral patterns and height anomalies that define an eddy, even when those patterns are partly obscured by other waves and currents. That lets us build a more detailed map of how the ocean breathes in both heat and carbon. The same pattern recognition tools are now being pointed at Earth's biosphere. In ecology, one big challenge is simply counting living things over large areas. How many trees are there in a given forest, and how healthy are they? Where exactly are different coral species located within a reef, and which ones are bleaching as ocean temperatures rise? High-resolution satellite and drone imagery provides the raw pixels, but individual humans can only annotate so many photos. Convolutional neural networks trained on smaller regions where we have ground truth, actual field measurements, can scale that up. They can learn to differentiate tree species based on subtle differences in canopy texture and color across seasons, or distinguish a healthy coral head from a stressed one by its spectral signature in the blue and green wavelengths. That, in turn, feeds back into our models of carbon cycles, biodiversity loss, and ecosystem resilience. We're not just seeing a green smear labeled forest, we're seeing a dynamic, pixel-by-pixel inventory of life. This raises an important question. If AI is now doing so much of the seeing, what are humans actually doing? The answer is, we're asking the questions and we're interpreting the answers. An AI system can tell you that a certain combination of pixel values is anomalous, or that a particular light curve looks like a planet transit. But it doesn't know what a planet is, or why methane matters for climate, or what it means for a coral reef to bleach. That's where domain knowledge, actual physics, chemistry, biology, geology comes in. Scientists design the training data. They decide what counts as a positive example and what doesn't. They check whether the AI is latching onto real, physically meaningful features or just learning shortcuts and artifacts. There's a whole field called interpretability research that tries to open up these black boxes and relate what the model has learned back to human concepts. In astronomy, for instance, people have used saliency maps to see which parts of a galaxy image most influence the AI's classification and found that they often correspond to regions like spiral arms or central bulges that astronomers already consider important. That's a good sign. The machine and the human are converging on the same underlying structure. At the same time, AI sometimes points us to things we didn't know to look for. In radio astronomy, for example, surveys like those from the Canadian Hydrogen Intensity Mapping Experiment have revealed fast radio bursts, millisecond-long flashes of radio waves from distant galaxies. Their origins are still debated, with leading candidates including highly magnetized neutron stars, called magnetars. Because these bursts are so brief and buried in noise from human technology and natural sources, finding them is like trying to hear a single faint click in the middle of a stadium full of people shouting. Machine learning classifiers can be trained on real bursts and known false positives, like airplane radar or satellite transmissions. Once trained, they can sift through millions of candidates and surface the rare, genuine astrophysical events. Sometimes they even find patterns, such as repeating bursts from the same location, that challenge existing theories and force us to refine our models of extreme physics. So, across space, Earth, and nature, the role of AI is surprisingly consistent. It is an amplifier of perception. It extends the range of what can be noticed, correlated, and tracked, far beyond what unaided human brains and traditional algorithms can manage. But it is also a filter. It decides which few out of millions of data points are worth our finite human attention. That makes it incredibly powerful. And also, something we have to understand and calibrate carefully. Bias in the training data or blind spots in the model can mean entire classes of objects or phenomena remain invisible, even as we congratulate ourselves on how much we're seeing. The universe has always been bigger and more complex than our instruments. Now we've built instruments that learn. The question is, what exactly are we teaching them to notice? Because when we give our machines new ways to see, we also discover entirely new kinds of cosmic and earthly creatures that we didn't even have names for before. And that's where the story of the hidden universe really starts to get strange.